General Chemistry 2 is more than just a continuation of General Chemistry 1. It's also building upon the principles that we learned in a previous semester. As a result, a review of the material expected to be carried on into General Chemistry 2 is imperative. For example, polarity gives us an opportunity to review several concepts, namely electronegativity, Lewis structures, Vesper theory, polarity itself, determining valence electrons, etc. Let's determine the polarity of SeO2, selenium oxide. Let's determine, is this a polar molecule? In order to do that, we first begin by drawing the Lewis structure and subsequently using Vesper theory to determine the molecular shape. So, valence electrons for selenium and oxide can be obtained by looking at the periodic table. If you do, you find that both are in group 6, and thus each have 6 valence electrons. So the total number of valence electrons for selenium oxide is 6 coming from selenium, and then 2 times 6 coming from oxygen, for a total of 18 valence electrons. Now, the first thing you do when drawing Lewis structures, after determining the number of valence electrons, is you place the more electropositive or least electronegative atom in the center. In this case, it's selenium, because we know that fluorine, oxygen, and nitrogen are the 3 most commonly accepted atoms as being the most electronegative. Secondly, you adorn the skeleton of your structure with the rest of the atoms, in this case, the 2 oxygens. You do so by drawing one single bond and thus using up 2 electrons per bond for a total of 4 electrons from our 18 valence electrons. This leaves us with 14 electrons with which to distribute throughout the molecule. We do that first on the exterior atoms. So we can put 6 electrons on each oxygen as lone pairs, each having 3 lone pairs. This allows us to use up 12 plus 4 for the 2 bonds, which leaves us with 2 electrons, which we then, and only then, distribute to the center atom. Now, the next step is to determine whether or not each atom obeys the octet rule. We can look at the oxygens, which are both equivalent on the outside, and see that we have 2, 4, 6, 8. However, the selenium atom in the center only has 2, 4, 6. In order to satisfy the octet rule, we can take electrons from one of the oxygens and use them to form a double bond between selenium, giving us a structure, a Lewis structure, which looks like this, with a double bond to the oxygen. Now, we could have done this for either oxygen because they are equivalent. However, we'll continue our discussion on polarity using this structure. Now we see that each atom satisfies and obeys the octet rule. And this gives us a good approximation for what the Lewis structure is for selenium oxide. Now, we know that, again, fluorine, oxygen, and nitrogen are the 3 most widely accepted atoms as being the most electronegative. Thus, we know that there's likely a partial negative charge on each oxygen atom and a partial positive charge on the center atom, selenium. Now, if this were the molecular shape of the molecule, this would be nonpolar, because each oxygen is withdrawing electrons towards the center of their atoms from selenium. However, Vesper theory allows us to determine the molecular geometry of this molecule, and we can identify this lone pair that exists on selenium. So rather than being a linear molecule, you get a distortion pushing down these bonds and subsequently these oxygen atoms for a more accurate 3-dimensional structure to look like this. As a result, you have a net overall dipole that is downwards. So if asked, is selenium oxide a polar molecule, the answer is unequivocally yes. Dissociation, or disassociation, is another important concept from General Chemistry 1, which will be useful moving forward in General Chemistry 2. Take a look at these two molecules. We have ammonium phosphate and silicon tetrachloride. Now, if you took these two molecules and dissolved them in water, which one would separate into ionic components, and which one would remain associated? In order to determine this, we need to look at the properties of the two different molecules. Ammonium can be written as NH4 plus, because it is a polyatomic cation, and phosphate can be written as PO4 3 minus, because it is a polyatomic anion. As a result, we know that when dissolving this ionic compound in water, it will dissociate into its respective parts. For example, you will produce 3 ammonium ions, all singly charged, and 1 phosphate ion with a triple negative charge, which is balanced out by the molecular formula. Now, silicon tetrachloride is a covalent compound. As a result, when dissolved in water, it does not dissociate. In fact, there's no reaction that occurs. You do not get ions formed via the dissolution of silicon tetrachloride. One of the topics from General Chemistry 1 that will be useful to carry over into General Chemistry 2 is the idea of enthalpy, or specifically thermodynamics. Consider the question above. How much heat is required to warm 27.5 grams of water from 0 degrees Celsius to 17.5 degrees Celsius? We're given the specific heat capacity of water, which is 4.186 joules per degree Celsius times grams. This tells us that it takes 4.186 joules, that's the amount of heat, that's the amount of energy required to raise 1 gram of water exactly 1 degree Celsius. Now, if you remember from our discussion in General Chemistry 1, there's an equation that allows us to determine how much heat or how much energy is required to warm water. And that equation is Q equals mc delta T, where Q is the work required, or the energy, or as chemists measure it, the heat, times is equal to the mass in grams times the specific heat capacity times delta T, which is the change in temperature. Now delta T can be solved by knowing the final temperature and subtracting from that the initial temperature, Tf minus Ti. And we're given the initial temperature, we're given the final temperature, we're given the mass, so as a result, we should be able to solve this problem. First, in order to determine the change in temperature, we know that our final temperature is 17.5 degrees Celsius minus 0 degrees Celsius for a total change in temperature of 17.5 degrees Celsius. Now, we can plug in our values of 27.5 grams times C, which we're given, the specific heat, 4.186 joules per gram degrees Celsius, times 17.5 degrees Celsius. We look and we make sure that our units cancel out. Grams cancel there. Degrees Celsius cancels here. We'll be left with joules, which is good because heat is measured, and that's how we compute work as an energy, a value of energy. When you plug this into your calculator, you'll get a value for Q, or the heat required to raise this amount of water 17.5 degrees Celsius as 2,015 joules, or, converting it to kilojoules, 2.015 kilojoules. Acids and bases is a topic featured prominently in general chemistry too. As a result, let's do a quick recap. So, consider the question, how many milliliters of 0.0875 molar H2SO4 completely neutralizes 50 milliliters of 0.135 molar sodium hydroxide? Now we can write the neutralization reaction out like this. We know that neutralization reactions produce water and the composite salt formed via the displacement of the cation from sodium and sulfate. Sulfate is a polyatomic anion with a 2- charge. Sodium typically has a 1+ charge, so we need 2 of those to make sodium sulfate as a neutral salt. Now we need to balance our equation. We do that by looking first on the left-hand side. You see that you have 2 sodiums, 1 sodium, and on the right you have 2. So we should add a 2 in front of sodium hydroxide in order to get a balanced equation. This now tells us that we have two hydrogen atoms here and 2 here for a total of 4 on the reactant side. Therefore, on the product side, we also need 4. So in order to do that, we can add a 2 in front of water. So now we have a completely balanced equation. Now, the next step is to determine exactly how many moles of sodium hydroxide we're trying to neutralize. So we can do that using the relationship that molarity times volume gives us the number of moles. Now, if we plug in our values, 0.135 molar times 50 milliliters is the same as 0.05 liters. This will give us the amount of moles of sodium hydroxide as 0.00675 moles of NaOH. Now, from our balanced equation, we can clearly see that for every 2 moles of sodium hydroxide, you only need 1 sulfuric acid in order to perform this neutralization. Therefore, that is our stoichiometric factor, 2-to-1 relationship. So now we can determine how many moles of sulfuric acid we need using that stoichiometric relationship and doing some stoichiometry. So, if we have 0.00675 moles of NaOH, we can multiply that by 1 sulfuric acid for every 2 NaOHs. The NaOHs are going to cancel out, and we'll get the amount of moles of sulfuric acid that we need in order to complete this neutralization reaction, which is 0.0033375 moles of NaOH. Of H2SO4, sorry. Now that we know exactly that we have 0.003375 moles of sulfuric acid required to react with this solution of sodium hydroxide, we can use the relationship that molarity equals moles per liter in order to determine exactly the volume in milliliters of this sulfuric acid concentrated solution is required to react in order to complete this neutralization. So in order to do that, we need to manipulate the equation m equals moles per liter to solve for moles, to solve for liters. We do that by multiplying both sides by liters, and then we get L times m, liters times moles, liters times molarity, equals the number of moles. Then if we divide both sides by the molarity, here they will cancel out, just as liters canceled out here, in order to sequester liters on one side of the equation as moles divided by the molarity. Now, we have all of these values. We have the molarity of H2SO4. We know how many moles that we need. So we can then determine the amount of liters as 0.003375 moles divided by 0.0875 molar to give us the amount of liters, which if you plug that into your equation comes out to be 0.039 liters, or converting to milliliters as the question asks, 39 milliliters.